All right. So, signals and systems. Today's lecture number 6. The section is 450, and today is Sunday, 28th day of January. The time is 10:30 to 12 in the morning. Last time, we learned how to plot uh, the signal that is both shifted in time and scaled in time as well. So let's say we have a signal x and we are transforming the time domain such that in the parentheses it becomes at minus b. Okay, suppose we know the graph of x. How do we plot the graph of y? For example, if x is this graph. Oh, sorry. If the graph of x is let's say alpha 0 and beta and 1, suppose this is the graph of x, then how do we plot the graph of y? Case 1, so what we do is we're going to pull the factor a out of the parentheses. Okay, so it becomes a, and inside the parentheses would be t minus b over a, right? So the first step is to obtain or plot the graph of x of at. So there are two cases for this. All right, the first case is when a is greater than 0, and the other case is when a is less than 0. When a is greater than 0, the graph would not time reverse, so the direction, the horizontal direction of the graph would still intact. All right, means that we don't do time reverse on the horizontal or time axis. But when a is less than 0, then we have to reverse the graph horizontally. We have to flip it 180 degrees around. So let's say that in the case that let's assume that a is greater than 0, then the graph of x would be, this is time and this is time. So what we do is we divide the scales on the time axis by a. So this point alpha would become alpha over a in this graph, right? So it becomes alpha over a, and beta would become beta over a. Alright, and the graph looks the same. Everything also looks the same. Because the other point, there is another point at time 0. At time 0, so 0 becomes 0 over a, which is also 0. So this point would stay exactly at the same time. So this is 0. And this graph is x of at. And then the second step, this case is when a is greater than 0, right? But if a is less than 0, then we know that we have to flip it 180 degrees around. So alpha would become minus alpha over a. and the graph will be like this. Right? Because when a is less than 0, then alpha over a would have to have another the other sign, right? If this is negative, if a is less than 0, then alpha over a would become positive. And so alpha over a would be here, and beta over a would be here. And 0 is still 0. And this is when a is less than 0. Now the second step is to shift whatever we have from the first step to the right by b over a. Now if b over a is positive, then we have to shift it to the right. But if b over a is negative, then we'd have to shift it to the left. So the second step would be shift x of at that we have, okay, by b over a. If b over a is positive, then right shift, we do the right shift. If b over a is negative, then we do the left shift. So the above graph, if b over a is positive, it will become this. You shift it to the right if b over a is positive, but if v over a is negative, then we shift it to the left. This case is when a is positive and b over a is positive. This is when a is positive and b over a is negative. Right? So there we have it, yt and yt. And the other case when a is negative is the same, shift left or shift right, depending on the sign of b over a. So that's what we learn from time transformation of a signal. Okay, for example, if you are given this signal, suppose we are given this signal, okay, where it is this. Suppose this is x. This is x. And this is 5. This is negative 5, 0, 2, and minus 2. Given x below sketch, y, which is x of 2 minus, I'm sorry, x of 3 minus t over 2. Okay, now in this case we see that y is x of minus 0.5 t plus 3, right? So the first step that we do is we pull minus 0.5 out. So we have minus 0.5 and the inside would be t minus 6. T plus 6. 3 minus t minus 6. Sorry. T minus 6. So the first step is to plot x of minus 0.5 t. X of minus 0.5 t is a scaled version, is a time scaled version of x. So x is minus 0.5 t, but we have to also flip it around the horizontal axis by 180 degrees. So this is x of minus 0.5 t. Now 5 here would have to be divided by minus 0.5, and after we do that we get minus 0.10. So this is minus 10, and minus 5 divided by minus 0.5 is 10. So this is 10, right? And then this graph, all right, would have to be here. It will look like this because we have to flip it around. Remember, because this is negative, right? We have to flip it around. So we'd have this. Sorry. We have this. And this line has to also be flipped around, so it will look like this. So we have the other one here. So this is x of minus 0.5 t, and there's nothing changes on the y-axis. So 2 and minus 2 would still be the same. And so this is x of minus 0.5 t. And the second step is whatever we have to shift it. In this case, shift it to the right because 6 is positive, right? You have to shift right this guy 6 time units. So after we do that, after we shift it to the right by 6, all right, sorry, here, this is x of minus 0.5, right? So we have to shift it by 6. So we shift it by 6. It would become this guy. Okay, because minus 10 would become minus 4. 10 would become 16. And 0 would become 6. So we have minus 4, 6, and 16. All right, and this is minus 2, and this is 2. So this is x of minus 0.5 t shifted to the right by 6 time units. And this is y. Okay, so there we have it. Right, so this is a review from last time. If you guys have any questions, please say it out loud so that I can know and I can help you with that. Any question? No? All right. So this is the summary table, right? We have three operations: shifting, scaling, and reflection. And we also have shifting in time and shifting in amplitude, scaling in time, scaling in amplitude, and reflection in time and reflection in amplitude. So whatever we do shifting, uh, whether it is a time shift or amplitude shift, we are adding something to something. If we are shifting in time, we are subtracting time t0 that we want to shift to the variable time t. All right, but if we shift in amplitude, we are adding something to the value of x. This is amplitude shift. We do it outside of the parentheses, but if we do time shift, we do it inside the parentheses. Scaling as well, if we want to do time scaling, we do it inside the parentheses. Okay, so we multiply the variable t by some factor that we want to scale. But if we do the amplitude scaling, we are multiplying to the value of x outside of the parentheses. Reflection as well, if we are doing the time reflection, we are changing the sign of the variable t. But if we are doing the amplitude reflection, we are changing the value, the sign of the value of x. All right. Okay. Right. So this is the summary. Okay. Now, addition of signals. All right. Suppose we have two signals. We have x and y. We are adding these two signals together. Here we are adding x and signals x and y together, and the result would be another signal z. And the value of the signal z would be the value of the signal x and y added together at the same time. Suppose we are adding we are evaluating the value of the signal z at time 0, then we have to plug in time equal to 0 in both x and y and obtain those values and then add those values together, and the result from the addition will be the value of the signal z at time 0. And this is the diagram that we use for adding the signals. We usually use a circle, right? Circle symbol to mean that the signals x and y are added. As an example, let's say that we have two signals x of t equal to 5 plus t squared when t is from -3 to -1. All right, and then 3 when t goes from -1 to 5, and then -10 when t is greater than 5, and then 0 else. And suppose we have another signal y, okay, which is 1 when time is greater than 0 and 0 when time is less than 0, and we want to add these two signals together. Find signal z equal to x of t plus y of t. Now the trick here, okay, I'm gonna teach you the trick to do this. Okay, the trick is to draw the time axis t, okay, and locate these points here, right? So for x we have -3, -1, 5, 3 points for x. So -3, -1, and 5. Now x when time is from -3 to -1, x is 5 plus t squared. So let's write it down. 5 plus t squared. This is x. Okay, it's a closed interval, and over the interval -1 to 5, x is 3. So x is 3 here. It's an open interval. Okay, and when time is greater than 5, x is -10. So -10 here. Okay, open interval, and then the rest is 0. So the rest would have to be here, and it has to be an open interval. Now for y, we only have time equal to 0, so let's mark it down. The time equal to 0 would be here. And when time is greater than or equal to 0, so let's put it a close interval marker here. Y is 1. And when time is less than 0, y is 0. So now we have to add them together. Okay, over this interval, okay, both the blue and the red are 0. So over this interval, the result would be 0. All right. Now, over this interval, x is 5 plus 3t squared, but y is 0. So add them, we get 5 plus t squared. 5 plus t squared. Okay, it's closed interval. Closed interval. This is open interval. And now, things become more interesting when we are in this interval, because in this interval, in there are two subintervals. The first subinterval goes from -1 to 0. X is 3, whereas y is 0. So 3 added by 0 is 3. So we have 3 here. And the interval would have to be open and open. Now, over this subinterval, y is 1, x is 3. So close interval here and close interval here. 3 plus 1 is 4. Now as for the rest, okay, x is -10, y is 1. So it would be -9 for the rest. So now we have z, all right? We pick them up. The first one would be t squared plus 5. T squared plus 5 over the interval starting from -3 ending at -1. So -3 less than or equal to t less than or equal to -1. Now the second interval would be this one, all right? 3, z becomes 3 is z is 3 when time goes from greater than -1 to less than 0, right? And z is 4 when time starts from 0 ending at 5. 4, 0 less than or equal to t less than or equal to 5. And then -9 when time is greater than 5. -9 when time is greater than 5. And the other one, the last one, let's not forget about 0 here. So 0 when time is less than -3 or else here. So this is the signal z that results from adding x and y together. Alright, so what we basically what we do is we do the interval analysis. All right, you have to mark down all the points, all the markers in these intervals for x, and all the markers in these intervals for y. All right, and then mark the values in each interval, and then we do sub intervals one by one, and then add those values in each of the subintervals together to get the values of z, and then we can have the result of the signal z of t. Okay, so we do interval by interval basis. Now another example, we are adding a sinusoidal signal with a square wave signal. Here in this example we do it algebraically, but in this example we kind of like do it geometrically. Signal x is a square wave denoted by the blue uh, graph here. It is a square wave, whereas signal y is a sinusoidal wave denoted by the red graph here. So we are adding them together. Now over this interval, x is negative, right? So we are adding a -4 to the red line. When we add -4 to the red line, we are shifting the red line down by 4. So this was the red line, and when we shift it down by 4, we got this signal. We got this line, right? This is the result from adding the blue line here, okay, with -4. So we're, basically we're shifting it down by 4. So it is shifted down by 4. And now whenever x is positive, see, whenever x is negative, we shift the signal y in that interval down by 4. So that's why we have this. All right. But whenever x is positive, we're shifting the red line in those intervals up by 4. So here y goes from this graph, right, shifted up by 4, so it becomes this. Now we connect these lines together to get the signal z. Okay, right, the shape of the signal z depends on whether x is positive 4 or negative 4. When x is positive 4, we shift y up by 4. When x is negative 4, we shift y down by 4. Okay, in that interval. Now let's look at this one. We're adding the signal x and y. Again, when x is positive 3, we are shifting the signal y up by 3. And the result will become this, right? We're shifting the signal up by 3. Okay, but when is -3, when x is -3 over these intervals, when x is -3, we're shifting the signal y down by 3 in these intervals. So that's why we have this x shifted down by 3. Connect them together, we get the signal z that is a result from adding x and y together. Okay, so I hope that's not too difficult. Now what about this? Okay, and this is more interesting and a little bit more complicated because there are overlaps, right? There's a lot of overlaps between x and y. So we have to break the overlaps, right? We have to break the overlap. The first subinterval here, this is the first subinterval. Y is 1.5, x is 0. So after adding them, we get 1.5. So I'm gonna do the shading. I'm gonna use a pink shading. Okay, this interval. And adding a red and blue together, we get a black one, which is z here. Now the second interval, let's use the blue interval here. Oh, sorry, blue interval. Here, you see, blue. The reason why I picked starting point here and ending point there, because right here the value of y changes, right, dropping from 1.5 to 0, so I have to end it here. That marks the end of my second interval. So the blue line is here, the blue interval is here. Now in the blue interval we're adding 1.5 and 1 together, and the result is 2.5. Now the third interval, let's use the green one. The third interval is kind of tiny here, little interval right here. This green interval, okay, is where x is 1 and y is 0.5. See, x is 1 in the green interval and y is 0.5. So we add them together, the result would be 1.5 in the green interval. So let's paint this interval as green. Now the next interval would be this little interval here, right? So let's mark it with a gray one. The next interval is right here. So in the next interval, right here. So in the gray interval, y is 0.5 whereas x is 0. So adding them, we got 0.5. Alright, so we do this all the way, right? We do this for every sub-intervals, and the next one, I'm going to do a couple more. The next one would be pink interval, and the pink interval. Now in this interval, y is 1.5, x is 0, so if you add them, you're gonna get 1.5 here. Now the next one is let's use a blue one. This is the next one. Okay, it's easier to shade it. This is the next one, and the next one here. You see, in the next one, y is 1.5 whereas x is 1. So if you add them, you get 2.5, and so on. So if you add x and y together, you're gonna get the black signal z here. So you get the idea, right? Where you have to add them interval by interval basis, right? You can't skip them. Another signal, another example. Okay, suppose x is 2 cosine of 2 pi 5t, and y is x shifted up by 5. This means that x is shifted up by 5, and this is x is sinusoidal with period of 1/5 and amplitude 2, and then phase shift is 0. Okay, and z is x shifted down by 5. So this is x. This is x. All right, you can see that the period of x is about 0.2. 1/5 is about 1/5 of a second, and the amplitude of x is 2, so it goes from 0 to 2, and then from 2 down to negative 2, and go up from negative 2 to 2 again. And y is x shifted up by 5, so the graph of y is the green one, is the graph of the blue graph shifted up by 5, so it's the green one. And the red graph is the graph of z, which is x shifted down by 5. So we kind of shift the whole thing, push it down by 5 units to get the z. Now the constants here, 5 and minus 5, are called DC offsets. Okay, minus 5 and 5 are usually called the DC offsets. Okay, in the labs, into lab 213 lab, when you are adjusting, when you're working with a function generator, you can adjust the DC offsets. Basically, what you do when you're adjusting the DC offsets, kind of like you're shifting it up or down. You're shifting it up or down. Okay. Another one, we're adding signals x and y together. All right, x is 5 cosine something, and y is 4 cosine something, and the period of x is 1.5 1 over 5, and the period of y is 1 over 4. So we're adding them to get the signal z. Now I added them in MATLAB, and the signal z is the black signal. Sometimes when you add two sinusoidals together, it might be easier, okay, to use trigonometric in the identities. All right. Yeah. Okay, so let's say, hey, if I can do that. Okay. Right. You see, if you add them together, if you remember, the result would become periodic as well, because both of these are rational numbers, and you can always find the least common multiplier of these two numbers. So LCM TZ would be LCM of T of 1/5 and 1/4, and the LCM of 1/5 and 1/4 is 1. So you see the graph of Z, the black graph, is periodic with period of 1. You see, you go from here to here, that's one period, right? Can you see that? And over interval of 1. Okay, and you can pick any point. You can pick this point, right, to go from there to there. That's also one period, and the period is 1. You see, or you can pick this point and this point, and you can see that the period is 1 as well. So Z is periodic. Basically, it is not a sinusoidal signal. It doesn't look like a sinusoidal signal, but it is a result from adding two sinusoidal signals together, and it is periodic with period of 1. Okay. Here, another example. I'm gonna do this one algebraically. So remember how we did it last time. When we add these two together, when we add these two signals together, we kind of draw the time axis, and then we mark the important points of x, right? So x has only one point, which is 0, so we mark 0 here. All right, and when time is positive, x is t plus 2. Okay, we have to mark it close interval because it includes 0 as well, and otherwise x is negative, x is 0, so put an open interval here. X is negative, x is blue, and y, for y we have 2 points, 0 and 2, so let's mark another point here, 2, and to going greater than 0, greater than or equal to 0 but less than 2, so y is the red one. Greater than or equal to 0 but less than 2, here, less than 2, y is 2. If you have greater than or equal to 2 here, okay, so I mark it with a close parenthesis, y is 2t minus 1, so we have 2t minus 1, and otherwise is this open parenthesis at 0, otherwise y is 0. Now we add them together interval by interval, so the result would be open interval 0, and then close interval and open interval here, and t plus 4. Okay, and then close interval and 2t 3t, sorry, 3t plus 1. How come do we have 3t here? Because over the in this interval y is 2t minus 1, whereas x is t plus 2, so add them together, you get 3t plus 1. So this is z. So let's summarize. Z going negative, t is less than, when t is greater than or equal to 0 but less than 2, z is t plus 4, this one, okay. But if t is greater than or equal to 2, here, greater than or equal to 2, here, z is 3t plus 1, okay. And then the rest is less than, when time is less than 0, which is otherwise z is 0. So here, so there we have it, the signal z that results from adding x and y together. All right, any question, guys? No? Okay. Now, the next one is multiplication of signals. We had addition, right? Multiplication is basically the same. Instead of adding them together, we multiply the values of them together. Interval by interval. Okay, interval by interval. So let's say we have x and y. We use this symbol, and we kind of like have a cross symbol indicating that it is a multiplication operation inside of the circle. So the result that comes out of the circle indicated by the leaving arrow, that is the signal z, which is x, the product of x and y, right? So for example, if x is 2 times cosine of 4 pi t, so let's think about it. This signal is sinusoidal, right? Sinusoidal signal with period of 1/2. Tx is 1/2, and amplitude of 2. So if you plot x, you're gonna get this, right? See the period go from here. How many waveforms are there? No, 1/2. Yeah, period go from here and here. This is one period. Okay, tx is 1/2, and the amplitude going vertical, right? This is 2, and this is x. This is signal x. And what about signal y? Signal u. U is 1 when time is positive, and u is 0 when time is negative. So u is 1 when time is greater than or equal to 0, and u is 0 when time is less than 0. Now we are multiplying them together. So the first subinterval is from 0 down. Okay. Now, in this subinterval, u is 0, so you don't have to think about it, because everything multiplied by 0 will become 0. Okay, 0 multiplied by anything becomes 0. So here, when time is less than 0, you get 0. That's because u is 0. Now when time is greater than or equal to 0, u is 1. So if you multiply 1 to x, you're gonna get x back, right? So whenever time is greater than 0, the product would be x. So this is the result from multiplying x and u together. Okay, so basically you have x, right? This is x when time is greater than 0, and 0 when time is less than 0. Okay, when time is greater than 0, you multiply 1 with this guy, right? And you get this. But when time is 0, when time is negative, you multiply 0 with this guy, and you're gonna get 0. Okay, so we have this graph. So it's basically, when you multiply something with this kind of function, it's like you're switching the signal x at time 0. The switch is closed at time 0, and switch is open before time 0. So this is what happens. You're kind of like, closing the switch at time 0, and the signal will go off. Now what about this? You have a sinusoidal. Can you see it is a sinusoidal signal? You have a sinusoidal signal here, and you want to multiply this signal by this rectangular pulse train. This is called a rectangular pulse train. It alternates between, the value of this y alternates between 0 and 1. Okay, it is 0 for some time, and then it is 1 for some times, and then it goes back and forth. So we multiply them together. Now every time this signal is 0, the product would become 0. So that's why we have 0 here. Okay, the 0 here occurs because this is 0, and we know that if we multiply this number 0 to anything, we're gonna get 0 back. Now every time when this signal is 1, here 1, right, 1, we're multiplying 1 to this guy in those signals, so we're gonna get this guy back in those intervals, right? So we get this. All right, you see, this is 1, right? So 1 multiplied by this, we get this back. So the product between these two signals has a graph that looks like this. This is the product. Okay, so it's like we are switching. We have a switch, right? We close the switch in these intervals. Otherwise, we turn it off. Then the output is 0. Okay, like we are. closing the switch, we opening the switch, we close the switch, open the switch, back and forth. Okay. Now another example. Okay. Let xt be equal to 3 cosine of 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 4 pi t minus 4 sine of 4 pi t. Now we want to plot this graph. Okay, we want to plot. The question is plot x of t. Now if you add these two together, right? If you add these two together, I think to plot this is kind of difficult because we don't know how to plot this, right? So the shape, the graph of x is quite unclear. But whenever you see things like this where the frequencies are the same, you see the frequencies are the same except that one is cosine, the other is sine, right? Think of the trigonometric identity. Okay, think of cosine of a minus b equal to cosine a cosine b plus sine a sine b. Also, cosine of a plus b equal to cosine a cosine b minus sine a sine b. So now what I'm gonna do is I'm gonna divide everything through by square root of 3 squared plus 4 squared. Okay, when I do that, I'm gonna have 3 over 5. Okay, cosine of 4 pi t minus 4 over 5 sine of 4 pi t. And then this reminds me of a right triangle. So let's draw a right triangle. This is 3. No, sorry. This is 3, this is 4. This is a right triangle, and this is 5, right? And the angle here is about 63 degrees. Okay, so if you look at this triangle, you're gonna see 5 here, and the inside is cosine of 63 degrees cos 4 pi t, and minus sine of 63 degrees and sine of 4 pi t. And then look at the green equation here. Okay, green, it's right here, the green equation here. You see, so it becomes cosine of 4 pi t plus 63 degrees. 63 degrees. So it is 5 times cosine of 4 pi t plus 63 degrees. So this is signal x. So now you can plot the signal x quite easily because it's basically a cosine signal, right? Shifted to the left by 63 degrees. So let's do it. How do we know it's shifted to the left? Now, look at this. This is equal to 5 cosine of 4 pi and then t plus. Now, what is 63? 63 is, if we want to turn it into radians, we have this is in degrees, right? So in radians we would have 63 over 180 pi, right? 63 over 180, so 6 radians. So 63 pi over 180 divided by 4 pi. Okay, and so this is 5 cosine of 4 pi. Inside is t plus. Now we can cancel the pi out, and then we multiply 180 with 4, we get 720. So t plus 63 over 720. Let's use my calculator. 63 over 720. That's about 0.0875. So that is 5 cosine of 4 pi t plus 0.088. 0.088. Now let's plot this one. Now if we plot this one, we're gonna start with the graph of cosine. Okay, the graph of cosine is this one. This is the graph of cosine. Is that right? Yeah. Rotate. Okay. I'm drawing the graph of cosine here. So this is the graph of cosine. Yeah, this is a pretty good. This is a nice graph. So how do we plot this? Let's start with the graph of cosine of 4 pi t. 4 pi t means that the period is 1/2. Period is 1/2. So period is 1/2 is this is 1/2. This is 5. This is -5. And this graph is 5 cosine of 4 pi t, right? And then we know that we have to shift it to the right by 0.088. Yeah, 0.088, right? 63 degrees. Let's see. 63 uh, uh, in radians divided by 180. 180 over 4. Yeah, 0.088. So I'm gonna copy this. How do I copy it? Oh, should. And you know that you have to shift it to the left, right? So here by 0.088, so it's about 0.1. So this color, let's make it blue color. Size, can we change the size? So the blue one is the graph of x. Yeah, you see shift left, right? Shift left by 0.088. So shift left means that this minus 0.088 here. Okay, so that's the graph of x. Okay, we kind of use this trick quite often. But the period is still 0.5. 0.088 over 0.5. Yeah, that's about right. Okay. Another one. Example. X of t. Now we're gonna see this often as well. So let z equal to x of t times y of t. So we know that it is t e to the minus t when time is positive and 0 when time is negative, right? Because when time is negative, x is 0. So 0 multiplied by anything is 0. So that's when time is negative. So now let's plot this one. Uh, this graph is I think we should start with negative time. When time is negative, z is 0. Okay, but this graph, when time is 0, is also 0, right? So it should start here. And now, does it have a, when time is infinity, when time goes to infinity, this guy will dominate, right? Dominate, because it decays faster than this one. Okay, e to the minus t decreases faster than t increases, so it will become it. This graph will go to 0 when time goes to infinity. So when we plot this, it will go up and then it will go down eventually. Let me do it again. It will go up and then it will go down eventually. Okay, and where exactly does this happen? Okay, where the maximum value of z occurs, where does this one occur, the maximum value of z? And what is the maximum value of z? Okay, let's see if I can do this. Okay, if I want to find the maximum value of z, right? So I have to differentiate z with respect to time. Okay, when time is greater than 0, when time is greater than 0, it becomes d of t e to the minus t, right? So I'm going to use the product rule, that is uh, e to the minus t dt by dt plus t. This is by product rule, and that is e to the minus t minus t e to the minus t. And that this point is where the slope of z is 0, right? Because when the slope of z is 0, that's, we know that is the maximum, the point where z is maximum. So if we set this is the slope of z, right? When time is greater than 0, this is the slope of z. So we set it to 0 to obtain this point, because we know that the slope at this point, the slope at this point is 0. So we have to set it to 0. Now, because e to the minus t is always positive, right? It does not go to 0. So we know we can divide it through by e to the minus t. So we're going to have 1 minus t equal to 0. And so t is equal to 1 when c is maximum. So we know that this point is 1. Okay, and what about this point? We have to just plug in t equal to 1 to z, right? And z maximum one times e to the minus 1. That is e to the minus 1. So it's about e to the minus 1 point 0.37. Okay, so this one is 0.37. Okay, so that is the signal z, right? We're gonna see this a lot as well when we study Laplace transforms. All right. Now, the last, if you have any question, please tell me so. Let's see how many people are there in this room. We've got 3 people. Ah, 3 people. Oh, we got 4 people. Wow. Oh, we've got 5 people.
Teacher, can I
Yes.
see the previous page?
The previous page, right?
Yes.
Sure.
Okay,
Anything?
thank you.
Anything in question?
Nope.
All right. Just tell me when you're done, all right? And then we're going to move on.
Okay, I'm done.
Okay. Now, the last one for today is the construction of periodic signals. The signal gt is said to be time limited in t if gt is equal to 0 for t not in the interval t. So let's see, for example, here, this is a time limited signal. If you plot this signal, right? If you plot this signal versus time, you see it is the value is 1 when time goes from -1 to 0. So -1, -1, and 0, and the graph is 1. Okay, the graph is 1. This is x1. You see, it is time limited. It is time limited. It has a value only within some certain interval. Outside the interval, the value of x1 is 0. So this is time limited, right? And what about this? This is sinusoidal, right? But it is a sinusoidal in just some interval only. The rest of the rest is 0. So let's draw this. Uh, uh, the period of this is what? The period of this is 4. Period is 4. See the period? You see why the period is 4? So we have, this is half period, right? Half period. This is half period. Yeah, half period. So this is x2. This is x2. This is 1. This is -1. So again, x2 is time limited. Now we are going to define another signal x by adding g together. But before we add g's together, we shift, you kind of like shift g by t0. Okay, we shift g in the multiple of t0, and then we add them together. So if we unfold this, let's see, x of t equal to summation going from minus infinity to infinity, g of t minus nt0, right? So this is just dot dot dot, right? Plus g of t plus 2t0 plus g of t plus t0 plus g of t plus g of t minus t0 plus g of t minus 2t0 plus dot dot dot. Okay, and this is when t0 is 0. This is t. Oh, sorry. This is when n is 0, n is 1, n is 2, n is minus 1, n is minus 2, right, and so on. So what we do is we put these graphs together on the same axis, right? And we add them. Okay, we add these graphs together. But because G is time limited, so they do not overlap. They don't overlap. So when we add them, it's kind of like you put them all together at once on the same axis, and they don't overlap, right? So let's see. Let now let this be G, okay? Let G equal to x2. So let me change this to x2. x2 x2 is this one. This is x2, and I have to change it to x2. x2. So let's plot this one. Now let's start with this guy. This guy is just x2, right? So I'm gonna copy this over. Okay, I'm just gonna copy this. So this is x2. This is n equal to 0. This is x2. This one is here. Now we shift x2 by t0 to the right, right? This is x2 shifted to the right. So it's this one. This guy here is this one. Now what about this? This guy is this graph shifted one hop, two hops. Okay, 2 times to the right. Each time we shift it by t0. So it will be this. Okay, and so this is 0, right? And so this is t0, and this is 2t0. Now what about this? Here we shift x2 t0 to the left. So we got this. Shifted to the left, right? And so 0 would become minus t0. This one is here. And this one is 2 hops to the left. 2 hops to the left. So we have this. Here. So this is minus 2t0. Okay, this is when n equal to 2, n equal to 1, n equal to 0, n equal to minus 1, n equal to minus 2, and so on. So you see, when I do this, I'm constructing a periodic signal. So this signal x is periodic signal, right? This is signal x. So you see, x is periodic with period t0, and each period of x is the signal that we use to construct x, which is x2. Okay, so here. Now, what is the power of x? So the power of x is just the energy of this one, right? Energy of one waveform divided by the t0. So that's why I write it down here. Okay. Any question? That's one way to construct a a signal that is periodic, right? With period of t0. Now, if you're not careful enough, if t0 is less than this interval, then the signal will overlap and you'll have a hard time. But if you pick t0 to be greater than the width of each waveform, then all of these will not overlap, and then it will become easier to draw. Okay, right. Now let's look at another example. Okay, are you following? Can I go to the next one?
Okay.
Okay, thank you. So let's look at another example. Now let's see. We have a signal G that is defined by this equation. So let's draw the shape of G first. Now G is T when time goes from 0 to 3. So 0 to 3. Okay? T is a straight line. T is a straight line with slope of 1 and passes the origin. So if you draw the graph of G from 0 to 3, you're going to get this. This is a straight line passing 0, passing the origin with slope of 1. Now the rest is 0, right? The rest is 0. So the rest is 0 here and here. These are the rest. So this is G. Okay, and let me this is slope. Ah, this is T, right? This is T. Slope of 1. And see, the width of G is just 3, right? And then we do this. We use G to define X. So what we do is let's put them together. Okay, let's put them together. Uh, X of T is dot dot dot, right? Plus G of T plus 6 plus G of T plus 3 plus G of T plus G of T minus 3 plus G of T minus 6 plus dot dot dot. Okay, this is when K equal to 2, K equal to 1, K equal to 0, K equal to minus 1, and K equal to minus 2. Now let's plot them. Let's plot these guys, and then we put them together onto the same axis to get X. This is X, right? This is G. This guy is G. Okay, so I'm gonna G is this one. Okay, we are kind of like carry this over the whole thing to here. Now the next one, well, let me mark it 3 here and 0 here. The next one, we shift this one to the right by 3 units. So 0 would become 3 and 3 would become 6 here. Okay, so this is 6. So this one is GT minus 3. And then the next one is GT minus 6 here. Okay, let me extend this axis a little bit to the right. This is 9. Okay, so this guy is here, and then and so on and so on and so on. Now, as for this one, we shift G to the left. Ooh. By 3 here. Okay, so we have this. Oh, sorry. We have this. Okay, so this is -3, and here we shift this guy 1 2 hops, right? So 6 time units to the left. All right, so here, and this is -6, and so on. Okay, we can't draw everything. It's just 5 waveforms. Here. So now this is the graph of the signal X that we constructed it from signal G, and it looks like a sawtooth signal. And this is 3. I forgot to mark it down, 3 here. Okay, this is an example of sawtooth signal. We call this one, it has a name, it is a sawtooth signal. The reason we call it a sawtooth signal is because it looks like a sawtooth. It looks like a saw, right? You use a saw to do something. Yeah, it looks like a sawtooth. So this is a sawtooth signal, and the period of it is 3, right? Period of it 3, and the power. If you want to find the power, okay, energy of GT is integrating. If you remember, from 0 to 3, GT squared dt, right? So integrating over this interval, G is T squared dt. So it is T cube over 3, going from 0 to 3. That is 9. Okay, that is 9. And so power of X is just 9 over 3, which is 3. And X is periodic. All right. Okay. So I guess that's it for today. We have come to the end of this sheet, and next time we'll begin another topic, which is various standard signals that you need to know uh, before we move on to systems. And then I think you're almost ready to do a homework, so I'm gonna assign the first homework to you on Thursday. Be prepared to do your first homework. And do you guys have any questions to ask before we leave?
ผมสงสัยหน้า16เอ้ย15มั้งครับน่าจะใช่
What page is that?
เอ่อ15ครับ
Yeah. Okay. What's it? What is it that you asking?
เอ่อที่อาจารย์บอกว่าถ้าเรียกแบบว่าอะไรสักอย่างหนึ่งครับมันจะไม่โอเวอร์แลปนี่คือตรงไหนครับ
All right. Let's okay. Give you an example. Suppose I define g of t equal to 1. Okay, let's make it simple, where t goes from 0 to 3 and then 0 otherwise, right? So let's draw this one. If you draw this one, you're gonna get here. This is 3, right? This is 0. This is 1. So this is g of t. Now, if I define x as g of t minus 2k. Now let's draw x. So if I'm gonna draw x, now when k is 0, I have g, right? So I'm gonna put g here. This is the case when k is 0, right? Right? So this is k is 0. Now when k is 1, I have to move this 2 units to the right, right? Because it is t minus 2 when k is 1. So if I move this to the right 2 units, it was here 1 unit, right? 2 units is here. 2 units, right? Do you see they are overlapping, right? Here they are overlapping because this number, the period that we are constructing x, is less than the width of g. So the width of g is right here, right? But we shift g to the right not far enough. The amount of the time that we shift g to the right is not far enough. So the blue one here does not leave the red one just yet, right? You see, it is trying to leave the red one, but it cannot do so because we shift the blue one to the right not far enough that the tail of the blue one doesn't leave the head of the red one. So you see there is some overlap going on here. So let's draw this. This is 3, this is 0, right? This is 5. Now let's draw k. This is when k is equal to 1. Now when k is equal to 2, again, when k is equal to 2, we are shifting the red one to the right by 4. You see, when k is equal to 2, we're shifting it to the right by 4. So let's make this one a green one. So 3, right? 4 is here. You see? 4. This is when k is equal to 2. And things like this will go on and on and on and on, right? And then if you add them together, your graph will look weird, right? You see what I'm talking about? Who's asking the question, please?
อ๋อครับผมก็จะ
Okay, all right. So this one is shifting it to the right by what? By 6, right? So 0 becomes 6 here. So when we add them together, it will be a constant, a DC constant, right? You got that, right? The reason is
ครั
because
บผม
this number 2 here is not big enough that if you put g on the same axis, they overlap. Okay, they overlap because this number is not large enough. It does not go beyond 0 to 3 here. The width here is 0 to 3. This number 2 is less than 3, so overlapping. Okay, that is what I talked about in page 15. Is that clear?
yes sir
Okay, good. Any other question, please? Okay, so thank you very much for attending, and for those of you who cannot attend, I've recorded a clip and then I'll post it on YouTube. I'll post the link on Classroom. You can take a look. And I'll see you guys again on Tuesday as usual in Classroom. I'm sorry, not in Classroom, on site at the university. Bye bye and have a great weekend.
ครับ
สวัสดี
สวัสดี
ค
ค
รั
รับ บ